Since the dawn of time, humanity has dreamed of mastering the skies. From Leonardo da Vinci's sketches to 18th century hot air balloons, the fascination with flight captivated both inventors and scientists. In the 19th century, pioneers like George Cayley and Otto Lilienthal advanced this dream by exploring aerodynamics and building gliders capable of brief, sustained flight. But the ultimate goal wasn't just to rise, it was to fly with control and autonomy. So how did we go from fabric gliders to massive aircraft that cross oceans in mere hours? The breakthrough didn't come overnight. For decades, inventors struggled to find an effective propulsion system until 1903, when the Wright brothers succeeded in creating the first controlled, powered aircraft. Their fragile wooden biplane only flew 36.5 meters, but it marked the start of modern aviation. Within 50 years, airplanes evolved from experimental crafts to essential tools for global transportation. The focus shifted from simply flying to flying safely, efficiently, and at scale. In the 1910s, small companies launched short-distance flights, mainly to deliver mail. But by the 1920s and 30s, aircraft like the Ford Tri-Motor and Douglas DC-3 were designed for passengers, improving range, capacity, and safety. By mid-century, airlines and airport networks grew, making aviation a real alternative to land and sea travel. The jet age of the 1950s revolutionized the speed and convenience of air transport. Once commercial air travel was established, aircraft design began changing rapidly to meet growing efficiency and safety demands. Jets introduced in the 1950s increased speeds, but required entirely new design principles. As aviation matured, innovations in materials, engines, and automation made airplanes more complex and adaptable. Building a plane today involves balancing physical forces, cutting-edge materials, and global regulations, a process that begins years before construction even starts. Modern aircraft design starts with critical factors like passenger count, range, and fuel efficiency. Engineers use 3D simulation tools to improve airflow and reduce drag by up to 15%. This led to revolutionary designs like the Airbus A350-900 wing, which can lift 280 tons with a 64.75-meter span. Structural improvements followed. Finite element modeling predicted stress points throughout the airframe. For example, the Boeing 787's carbon fiber fuselage was engineered to withstand internal pressures of 8.6 tons per square meter, meeting strict safety codes. At the same time, engineers integrated tens of thousands of systems, from controls to entertainment, ensuring performance in extreme cold or heat. This detailed work involved teams of thousands collaborating on digital platforms that updated blueprints in real time. This teamwork, combined with simulations and wind tunnel testing, cut development time from 10 years to 6, while keeping error rates incredibly low. This collaborative effort extended into production. Manufacturing became a global process. Each airplane part, from bolts to wings, is made to sub-millimeter accuracy on different continents. In 2011, the Boeing 787 Dreamliner became a milestone in global engineering, using parts from 45 countries. Wings from Japan, tail sections from Italy, and fuselage sections from the US. This method, called design for manufacturing, lowered costs and sped up timelines but demanded flawless logistics. Final assembly happens in megafactories like Airbus's plant in Toulouse, where human operators work alongside laser-guided robots. These machines drill 3,000 holes per wing in 12 hours, work that once took weeks and had high error rates. For crucial parts like the A350 wing spars, 5-axis machines cut 8-ton titanium blocks into shape. Removing over 90% of material in 40 hours. But perfect manufacturing isn't enough. Quality checks are extreme. Each part undergoes non-destructive testing to international standards. Ultrasound can detect 0.1 millimeter cracks in carbon panels, and thermal imaging checks engine welds. In 2018, a 3D scan of the Boeing 777X caught a 0.03 millimeter error in a wing joint, fixed before it could affect performance. Management systems like SAP track 4 million parts per plane, flagging any delays or defects instantly. This integration allows the Airbus A350 to be built in just 30 days, down from 150 in the 1980s. But the true innovation lies in the engine. Carbon fiber blades spin at 2,500 revolutions per minute, enduring centrifugal forces equal to 100 tons. Inside, ceramic-coated superalloy blades work at nearly 1,500 degrees Celsius, just below the melting point of steel. In the 2010s, GE Aviation introduced a microchannel cooling system that circulates air within the engine, extending blade life across thousands of flight cycles. This not only boosts engine performance but also reduces maintenance and increases safety. Sustainability is now key. In 2021, Rolls-Royce revealed the UltraFan with an 11-to-1 bypass ratio, cutting fuel use by 25%. It pushes 90% of airflow outside the combustion core, cutting both noise and fuel burn. Biofuels made from waste or vegetable oils can cut CO2 emissions by up to 80%. But require engine adjustments to prevent corrosion. The GE9X, built for the Boeing 777X, represents this evolution. With a 3-meter diameter and 510 kilonewtons of thrust, it's the largest and most powerful engine ever built, yet 15% more fuel efficient than its predecessors. After its first test flight in 2020, the GE9X faced delays due to the pandemic, but finally entered service in 2023. Paired with growing use of green fuels, these innovations are changing aviation, making it quieter, cleaner, and smarter. Electronics also play a vital role, serving as the brain of every flight. Since 1983's Airbus A310, glass cockpits replaced analog dials. Today, a Boeing 787's onboard systems optimize routes in real time, saving 2.5 tons of fuel per transatlantic flight. GPS and satellite systems like Europe's Galileo now offer sub-meter precision. Combined with X-band radar, pilots can avoid storms from over 300 kilometers away, even when visibility is low. Fly-by-wire systems, fully digital, adjust control surfaces 20 times per second. Airbus's A350 and Boeing's 787 use fiber optic networks to deliver instant, stable responses in turbulence. Cybersecurity is essential. Boeing added redundant systems in the 777X after 2018 cyber attack drills. Since 2020, the FAA mandates real-time location updates, reducing mid-air collision risk by 90%. In 2022, Airbus proved full automation in the ATOL project. An A350 took off and landed using AI, LiDAR, and infrared vision. While pilots remain vital, automation is shaping a future of safer, more precise flight. Yet progress comes at a steep cost. Airbus's A380 required $25 billion in R&D, rising to $32 billion due to delays. Each plane, priced at $445 million, cost $320 million to build. Mass production helps. The A320neo cost $110 million to make, thanks to economies of scale. Boeing's 787 Dreamliner cost $32 billion to develop, only viable after selling 1,300 units, achieved in 2020. Labor is another big expense. 3,000 Airbus workers in Toulouse earn 75,000 euros annually. Boeing workers in Seattle average $85,000. Certification also adds costs. Up to 2,500 hours of test flights can cost over $1 billion. Airbus ran 400 flights under extreme weather before launching the A350. These tests ensure aircraft can last 60,000 to 90,000 hours of service. Airlines cut costs by buying in bulk. Emirates paid $157 million per A380, nearly 60% off list price. Leasing, long-term contracts, and maintenance deals help airlines recover investments over 12 to 15 years. Even a 2% efficiency gain means $1 million in savings per year per aircraft. The goal now? Net zero emissions by 2050. In 2022, electric plane Alice flew 440 kilometers on lithium batteries. Airbus is building a hydrogen plane for 2035. But new tech needs new infrastructure, and airport upgrades are essential. Saudi Arabia is investing in this future through its Vision 2030. Its Neom Smart City project includes an AI-powered airport designed to reduce emissions. Though still in planning, these initiatives represent the path forward, where innovation meets sustainability.